Hello everyone, welcome back to our lecture on glaciers, Earth System 101. We're going to continue this discussion talking about glacial movement. So by definition, glaciers move, as you can see here with these time-lapse images. So there's a number of different types of movement that we can classify. The first type is ice deformation. So all glaciers will deform under their own weight. This is the dominant process of cold-based glaciers, since there's not a lot of sliding at the bed. You can see that here, this is a glacier in Antarctica, where the glacier has friction on the bed, and so there's not a lot of movement there, but there's still that weight of the glacier that pushes it forwards, especially near the top of the glacier, and so it'll slide forwards, deforming the ice as it does. And so the ice slowly moves faster at the surface and nearly zero velocity at the base, and you can have these deformation patterns that result. The next type of movement, glacial movement, is basal sliding. So this is usually most common in temperate glaciers, warmer-based glaciers where you have water flowing underneath the bed. And as a result, you can have the glacier just sliding over that bedrock and the entire glacier moving forwards instead of that velocity gradient that we have for ice deformation. Next, also, when a glacier is flowing over sediment, you can have bed deformation. So when the sediment is soft enough, the glacier can move just by deforming the sediment underneath it and causing it to slide forwards. You can see here this deforming horizon of sediment that's getting sheared by the glacier and allowing it to move forwards. And all three of these processes are usually going on to some extent on a glacier. And so the velocity of a glacier can vary significantly from one to the other. You can see here a very fast-moving glacier that's being sped up in time-lapse. But you can see a map here as well that shows the velocities of the Greenland ice sheet. And you can have widely different velocities all the way from tens of meters per day down to centimeters per day, depending on the properties of the bed, the properties of the ice, the weather, and a number of different factors. We can see some evidence of glacial movement even in a still photo. For example, these are ogives, these successive kind of rings on a glacier, in the Gilkey Glacier in this case, near the Juneau ice field. And so ogives form from ice falls. So the Gilkey Glacier is fed by a very steep glacier just over here, and that ice fall causes the ogives to form. And you can see a diagram of that here. When the ice comes at a higher velocity into that valley, you can have shearing occur as a result. And these shearing planes develop, and they cause these thrust faults within the glacier. And so as that shearing occurs, you have sediment that's brought up from underneath the glacier, and you can have these thrust moraines or sediment deposits that develop as a result in successive order, usually corresponding to 1 year of flow as another new thrust fault develops. So glaciers will move faster or slower depending on if it's winter or summer, and so that disparity in the velocities can cause that faulting, especially when you have that steep change in slope as you do in ogives and ice falls. So next, we're going to be talking about accumulation zone features. These are features of a glacier that form in the accumulation zone. So the accumulation zone, remember, is the zone of a glacier where you have net accumulation where the amount coming in is greater than the amount of ice leaving, the area above the equilibrium line, the ELA. And so I was up in the Greenland ice sheet accumulation zone these past few springs. And so you can see our tent site here where we were drilling into the ice and collecting ice cores. And so we were looking at firn. So firn is snow that has survived at least 1 year and still has interconnected pore spaces. You can see all those different pores here, these little spaces in the ice. So as snow falls, it gets compacted, and it gets more and more compacted until all of the area of the air in that snow gets compacted until there's no more pore space. And so eventually it reaches a point of compaction where the pores are no longer connected. And after that point, we call that ice. And before that point, we call it firn. So firn still has interconnected pore spaces, but it's still survived more than 1 year of melting. And sometimes we can have melt water that flows through the firn. So as you have melting at the surface, that water can percolate down into the firn and refreeze. And when it does, it forms these ice lenses. You can see me here holding an ice lens up to the sun, showing how translucent it is. And so these ice lenses can develop in the firn as you have refreezing of that meltwater. And that's really important when we look at it on the continental scale, because sometimes these ice lenses get so thick that we call them ice slabs. These are several meters thick ice lenses that develop and have been growing due to climate change. And when these ice slabs get so thick, they tend to block the firn below it from gaining more meltwater, and therefore that meltwater doesn't go into the firn and instead flows out as runoff. And so when you have thicker ice slabs developing, you have more runoff because that buffering that the firn would supply otherwise is not there anymore. And so that's something really to look out for. With more climate change and more ice slabs, you might have more runoff from Greenland. Another interesting thing about the firn is firn aquifers. There's a few areas in Greenland that we found where the meltwater that percolates into the firn doesn't actually freeze. And so it doesn't get cold enough during the winter to actually freeze into an ice lens. Instead, forms an aquifer, just like you would in soil. And so you can have large firn aquifers that develop, especially in southeast Greenland, where you have large stores of water that stays in the firn for multiple years. All right, so that covers accumulation zone features. Next, we're going to be talking about ablation zone features. These are features that develop below the ELA, the equilibrium line altitude, and are formed mainly due to melting and the flow of meltwater. So the first feature that we're going to talk about are cryoconites. Sorry, anyone that doesn't like seeing pictures of holes, but these are holes that develop in bare ice due to sediment and bacteria growing on that ice. So here's a diagram showing how they form. So you have sediment, usually dark in color, that gets piled up onto the glacier. It's just a small pile here, and that dark color allows it to absorb more solar radiation, more sunlight, and as it does, it melts into the ice and forms a hole, and that hole tends to be 10 to 50 centimeters deep and 1 to 75 centimeters wide, and it will form this little melt pond, little pocket of meltwater that kind of protects it from absorbing more radiation. And then at night, that little amount of water will freeze over, and you have a little ice cap over that cryogonite. And so that can happen several times over a glacier, and you can have these series of cryogonite holes that develop as more sediment and more bacteria blow onto the ice sheet. Another very important feature of the ablation zone is superglacial lakes. So superglacial lakes are lakes that develop on top of a glacier. And these are really important. One, because they are dark in color. You can see this dark blue color compared to the bright white color surrounding them, and therefore they absorb more solar radiation. They have a low albedo. Additionally, when a crack or crevasse develops underneath them, these superglacial lakes can drain rapidly. And rapid lake drainage events can cause the glacier to speed up and cause a huge outflow of runoff to the ocean. So they're definitely important for understanding the glacier mass balance. Another interesting feature of the ablation zone, especially for me in my research, these are pictures that I've taken, are superglacial streams. So these are superglacial streams in Greenland, southwest Greenland, that we study. And so these superglacial streams are streams that flow over the ice sheet surface. And so just like any other stream or river system, they drain an area, and eventually they reach their endpoint, which is usually a moulin. So a moulin is a hole that that a superglacial stream flows into that goes all the way from the surface down to the base of the glacier. So it's kind of a channel that the superglacial stream flows into and can reach all the way to the bed. So as it flows down to the bed, that channel is known as an englacial stream. So an englacial means it's inside the glacier. You can see some photos of some very brave researchers exploring a dried englacial stream. So these are streams that start in the surface and then go down to the bed and convey that water down to the bottom of the glacier. When they get to the bottom of the glacier, they become subglacial channels or subglacial streams. And you can see these beautiful photos here of subglacial channels. So the water that reaches the bed will flow along the bed-ice interface and then eventually out to the terminus of the glacier. There's a number of different types of subglacial channels. Maybe the most common would be Rutgers channels. And so these are channelized subglacial channels in which the water carves out a space into the ice and flows over hard bedrock. So the Rutgers channels always have this kind of curved structure into the ice instead of into the rock or sediment below it. Additionally, we can have distributed kind of sheet-like films that are draining the subglacial system. So when you don't have a preferred flow path, it just kind of flows evenly under the glacier. Next, we can have broad or low channels. These are just kind of distributed channels that flow under a glacier but don't significantly carve out into the ice. We can have cavities, which is a series of pools that develop underneath a glacier. We have nye channels. So nye channels usually develop in softer sediment. And so instead of carving into the ice, they carve into the sediment instead and will form and flow out that way, where the water is flowing over the softer sediment instead of under the ice. And then lastly, we have porous flow, where you have pore sediments, pore-filled sediments, such as sand that the glacier is moving under, and the hydraulic conductivity or the flow rate of the water through those sediments are high enough that you don't need to have channels formed, and you just have flow through those sediments. So those are the 6 different types of subglacial channels that we observe. And so subglacial channels are really important because they dictate the speed of a glacier. When you have a lot of flow going into subglacial channels, you can actually have the water pushing up the glacier. And you have a lot of pressure that builds up in these channels. And as that pressure builds up, it pushes up on the glacier and lifts it just a little bit. And that lifting allows the glacier to flow faster. And so, especially early in the season, when these channel networks aren't quite as well defined and still developing, when you have a flush of water into these systems, you can have a pretty significant increase in velocity of the glacier. And so knowing how these subglacial channels develop and how much water is getting fed into them is really important for knowing how much calving, for example, will happen at a tidewater glacier, and how much ice will be lost due to that increased velocity. So sometimes these subglacial channels will form ice caves. So these are ice caves that we explored in Juneau. So some beautiful ice caves. And so these ice caves can form these networks that go underneath the glacier and can extend for sometimes several miles into the glacier and can be explored. So next, let's talk about superglacial streams a little bit. So superglacial streams are streams flowing on top of a glacier. They're one of my favorite features on a glacier just because I study them specifically. So these are superglacial streams in Greenland from our study site, where we visit each summer to record the amount of flow through these systems. And so here you can see a Google Earth map showing where specifically our site is. So it's in southwest Greenland, right at the ice edge. And this is our stream that we measure here. And so you can see here that the stream is flowing just like a normal stream that you might experience on land. It has meanders, it has sediment deposits, just like these ones here, as it drains those cryoconite holes and has sediment flowing through it. And then eventually this stream flows into a moulin here, where it reaches the bottom of the glacier. And so one of the reasons why I study superglacial streams in particular is because they're particularly low albedo features. So the ice of the ice sheet tends to have an albedo roughly around 0.45, maybe a little higher if there's fresh snow that's accumulated on it as well. Whereas the water can have albedos as low as 0.21. And when there's sediment in that water, cryoconite that's flowed into those streams, the albedo can be reduced all the way to 0.09. So very dark in color. And when we have lower albedos, we have more solar radiation being absorbed and more energy goes into melting. So knowing how many superglacial streams there are and how much sediment is in these streams is really important for determining how much melting occurs within the ablation zone. And so one of the ways that we study these superglacial streams is with drone surveys. So we fly drones over the area and we use the imagery from the drones in order to make three-dimensional maps of the region. And then we also take GPS measurements that you can see here in order to know very detailed topography of the stream bed. And so, yeah, that's how we collect most of our measurements is with drones as well as high precision GPS. And using that information, we can make maps like this. So this is the clipped image of the superglacial stream that we just saw, just the imagery from the drone. And then we can classify that sediment or clean stream using GIS. So for example, we can see in the imagery that this area has a lot of sediment, and we can use GIS to classify it as such and get a percentage of the stream that's covered in sediment. And then we can use that GPS measurements in order to get the water depth, and we can relate the sediment that's being deposited to the water depth of the stream. And so one of the reasons why knowing this is really important is what we've found is that the cryoconite, the holes that develop on the ice sheet surface, tend to develop these granules. So these grains of sediment that get wrapped up in these long stranded cyanobacteria. And as it does, it allows that ball of sediment to get larger, and therefore the superglacial stream has a harder time flushing that sediment out. And so the fact that these sediments are getting balled up by these cyanobacteria means that there's significantly more sediment in the stream than there would be otherwise. And without this process of granulation forming these balls, then you pretty much would not have any sediment being deposited in these streams, and then the albedo would be significantly higher. And one of the ways that I study this process is through hydrologic modeling. We can use the GPS measurements of depth and the drone imagery and plug that into a computer system, a hydrologic model, in order to simulate throughout the day how much flow there is, and therefore predict how the albedo is changing for every single minute of the melt season. So it's a really important tool that we can use. So next, we're going to be talking about crevasses. So crevasses can be found all over glaciers and are really important features. These are us practicing crevasse rescues in a crevasse near Juneau. This is a fairly shallow crevasse, just ends right below this photo. So we can safely use it to practice crevasse rescues, but sometimes crevasses can be quite dangerous and something to look out for. So a crevasse, to define it, is just a linear crack in a glacier caused by the ice being under tension. So an ice can be under compaction when it's being smushed together, or under tension when it's being pulled apart. And so when you have ice under tension, you tend to have crevasses that develop as the glacier can't handle that strain. So there's a number of different types of crevasses. The first one is traverse crevasses. These are crevasses that go across the entire glacier, usually. And so you can see a diagram here. When a glacier flows over a bump and it experiences tension, the top of the glacier will fault or crevasse as a result. And so whenever it's flowing over a region and increasing in slope, that will occur. And you can see some examples of tension fractions in here as the glacier flows over a bump of some kind. Another important type of crevasse are splay crevasses. These are very common in Piedmont glaciers, for example. You can see all of these splay crevasses going out, and they're formed as the glacier spreads out over a region, and that spreading causes tension. So you have cracks going up the glacier from that source of spreading. Next, we have Bergstrom and Randkluft crevasses, named by the Germans. And so these are crevasses that normally form over hanging glaciers. So the Bergstrom crevasse is the largest crevasse in a glacier. You can see that here, and it's formed as you have that glacier just starting to initiate its movement and kind of breaking off and having more flow downstream. And then the Radcliffe crevasse is the crevasse that separates the glacier from the cliff face itself at the top of the glacier. And so these are the most prominent crevasses that you see on hanging glaciers. Next, we have radial or en echelon crevasses. So these are crevasses formed when a glacier slides past a rock surface or curves. So you can see here that this glacier is curving to the left, and as a result, there's tension on the right side of the glacier here, as that part of the glacier has to move faster than the inside of the curve. And as a result of that tension, you have crevasses all along perpendicular to the flow. You can also have en echelon crevasses form as you have friction against the side of a valley floor. And that friction will slow down the glacier along the edge, whereas it's moving faster in the center of the glacier. And that difference in velocity will cause tension and therefore crevasses. You can see some examples of radial crevasses here. This is a photo I took in Juneau, where you can see several radial crevasses on the side of the glacier, as well as in here and in here. And so radial crevasses can make up a large portion of the crevasses, especially in a very curvy glacier. Next, we have ice falls. Talked about this a little bit earlier, but ice falls are just like waterfalls, just with ice. They're an area where you have very steep increase in slope, and therefore the glacier can get broken up and flow down this steep area into the valley floor below. And so it's just a steep area of fast flowing ice. Next, we have basal crevassing. So basal crevassing occurs usually in tidewater glaciers, where you have a lifting force due to the buoyancy of the ice flowing into the water, and so you have less basal drag as you go deeper into the water, and therefore you can have tension develop as you have kind of that flotational force, buoyant force developing, and crevasses develop on the bottom of the ice. Crevasses can be made more prominent and can expand due to hydrofracturing. So oftentimes in crevassed regions, you have a lot of melting occurring as well. And sometimes the meltwater will flow into these crevasses and provide a pressure that opens up the crevasse even more. And so crevasses that have water in them have that additional pressure and tend to be larger and can crack more extensively. And that process is called hydrofracturing. And that was really important, for example, in Antarctica, where we had this catastrophic glacier loss. This is the Larsen B ice shelf that completely got disintegrated a few decades ago. And it was aided by the fact that there was a lot of hydrofracturing. This area has experienced a lot of melting, and you can see these meltwater filled crevasses developed, and when that got extensive enough, this entire ice shelf broke off, and now this whole area has been flowing faster and contributing more to sea level rise. And it's predicted that this might occur soon also in Larsen B, which is the next ice shelf south of this. And so next, we're going to talk about calving. Calving is a process in which a chunk of ice breaks off the terminus of a glacier, So you can see an example of that in Perito Moreno, the glacier that I showed from Argentina before, as well as in Greenland here. So in a uh, uh, glacier like this, you can have ice that breaks off, and you have ice loss, not because of melting, but because of the formation of icebergs. And there's a number of different types of calving events. We have topple events, like we see here, where you have a block of ice that just falls into the water. Additionally, we have drop calving events, where we have the waves lapping away and melting at the glacier, and then a crack developing and that whole block of ice just dropping down. We have seracs, where you have kind of a tower that extends out over the water and then breaks off and falls in a smaller chunk. And then we have subaqueous calving events, and that's when you have basal cracking, basal crevassing that we talked about. And you can see an example of a subaqueous event here, where the crack developed and it allowed the block of ice to lift up and roll backwards and get cut off. So when we have calving, sometimes we also have the formation of a melange. So a melange is just a slurry of icebergs and broken up pieces of ice that develop in a fjord outside of the terminus of the glacier, that fill up the fjord with this ice. And so that's really important for the ocean life that live there. It can cause a lot of unique habitats in this melange as different areas open up and the icebergs melt. And so it can kind of be a staging area for icebergs that leave the fjord and enter the ocean. And you can have a lot of melting here as you have a lot of surface area where the icebergs are heading the ocean. So that's calving, and we're going to take a short break here, and we'll continue this discussion talking about glaciers in the next video.